Okay, here we are. We are on 2-3, day 3. And you'll be happy to know this is not too long of a day, I think. Just going through 2 story problems in the book. Story problems get to be a little bit challenging, just in knowing what they're asking for. So our first example is number 20 on page 51 from your book. And you don't really have to have your book open. I'll show you real quick and then we'll write down the important stuff. We're doing the pizza delivery problem. Ida Livermore, haha, starts off on her route. She records her truck's speed and velocity in miles per hour at various numbers of seconds since she started. Show Ida that these data fit the equation velocity equals 5t to the 1/2. So all they're asking you to do here is plug some numbers in and show that you get the velocities here. So if t is 0, 0 to the 1/2 is 0, 5 times 0 is 0. 1 to the 1/2 is 1 times 5 is 5. That's all they're looking for there. The big calculus stuff is down here in B and C. So B. Well, first of all, let's get the table written down. So her times went every, oh no, not every, 0, 1, 4, 9, and 16 seconds. Her velocities were 0, 5, 10, 15, and 20, that's a 15, and those were in miles per hour. So the first part of this problem asks us, it actually explains, it says the truck's acceleration, we're on part B, is the instantaneous rate of change. So acceleration is equal to the instantaneous rate of change of velocity. That was nothing there. Okay. Estimate acceleration at time 9 seconds by using velocity at 9 and velocity at 9.001. Well, let's go back. I forgot to give you the velocity equation. Is given by 5t to the 1/2. So just t is to the 1/2 power there. Okay, first of all, rate of change. What calculus term are we talking about here? Derivative. For derivative, right back to chapter 1, we did derivative so far. I'm in chapter 1. It was our 3-point table and the slope of the tangent line. Here, well, we had that 2-point table, and that's what the author is asking us to do here. Just use 9 and 9.001. So we'll do that. 9 and 9.001, and we'll just do a 2-point table and do the rate of change. Change in y over change in x. Oh, I forgot to grab a calculator again. I'll use this one. Turn it up. Oop, too much. Okay. Y equals 5x raised to the 0.5. Same thing as 1/2. I want 9 and go by 0.001. So 9 is 15. And 9.001 at the bottom of the screen, again, you got a lot of zeros there, so we'll carry some of those out. 0.008333. So now we'll do change in y over change in x for that value. So 15.008333 minus 15. My change in time is 0.001. So I've got 0.0008333 divided by 0.001, 0.8333. And we need units. It is a story problem. So what we did here was we divided the y by the x. We do the same thing on the units. The y units are miles per hour, dividing by seconds. So we've got miles per hour per second. Ugly unit, but that's what it is. Okay, it says make a conjecture about the exact value of A9. Do you know what fraction this is? 0.83333, probably repeating. If you don't, 0.833333333 turn into fraction. Looks like it's about 5/6 is our estimate. Let's see what we got. Part C. It says A9 is exactly equal to the limits of, and I'm reading right from the book, so if you wanted your book open, you could. It's the limits of the velocity equation minus the velocity at time 9 divided by t minus 9 as t approaches 9. It says factor the denominator as the difference of two squares. Okay, our goal is to find this limit. And we just spent the whole section doing the limit stuff. So, substituting in limit as t approaches 9. Here we want the equation. What is the velocity equation? The velocity equation is, at the top of my paper here, 5t to the 1/2. 5t to the 1/2 minus the velocity at 9. Right from the table, the velocity at 9 is 15. All over t minus 9. If you put the 9 in right now, remember 1/2 power is square root. So the square root of 9 is 3 times 5 is 15. 15 minus 15, 0 over 0, which tells us we can factor this. So, and he tells you to factor the numerator and the denominator. The bottom is going to get factored as the difference of two squares. This is a little unconventional, but we'll get there. Up here, think of this as two baskets. You got a 5 and a t to the 1/2 and a 15. What can come out of the two baskets is a factor of 5. So when you take the 5 out, when I take it out, I divide it out, I'm left with the t to the 1/2 minus, you had 15, I divided a 5 out, that leaves a 3. And you know you did it right. If you distribute, you should get this back. 5 times t to the 1/2, 5 times the minus 3 is minus 15. The bottom. We don't really recognize this. If you had, let's say, x squared minus 9, you might be able to remember from algebra that that's the difference of two perfect squares, x and x, and positive 3 and negative 3. Because you have no middle term, and if you get a plus 3x and the minus 3x, that's what makes the middle term go away. You've got your minus 9, you've got your x squared. He wants us to think of this as the difference of two squares. Well, yes, 9 is a square number, but t isn't as obvious to recognize it as a square. And what you have to do, you know you'll have your minus 3 and your plus 3 for the 9, for the minus 9. But what t to what power times t to what power is going to give me t to the first? Well, if you think about it, when you multiply, you add exponents. What number can I add to itself to get me 1? Well, that's a half. And we knew we were going to match this factor up here. So now I can cancel out the t to the 1/2 minus 3's. And we are left with the limit as t approaches 9, the only thing left in the numerator is the 5. And the bottom we've got t to the 1/2 plus 3. Putting the 9 in, we'll get 5. That is the square root of 9 is 3 plus 3 is 6, 5, 6. And I think that's what we thought we should get. Okay. And that would be miles per hour per second. And then part D, this is just seeing if you know what this is asking for. Approximately how far did she travel between 1 and 9? Find the distance traveled from 1 second to 9 seconds. Okay, think about it. We've got velocity and time. What in calculus is going to give us this distance? Remembering that distance is velocity times time. In calculus, to multiply the two variables together, we do the integral. And we don't have the graph, but we've got that nice trap rule. So I would use the program here. I don't know if this calculator actually has it on there. These programs. Oh, maybe. Nope. Bunch of junk on there. Let me run and grab one real quick. I ran all the way back there and got one without it. I'm assuming you can run the trap rule by yourself. So go ahead and run the trap rule and write down what you get for distance there. Right. Next example is number 21 from your book. Number 21, same page. They're giving us a function, x cubed. It says find approximately the derivative at 2 by dividing the change in f of x from 2 to 2.1. So part A, find derivative. Find derivative at x equals 2. By finding the change from x equals 2 to 2.1. Okay, again, derivative, normally if it's left up to you, you do the 3-point table because it's more accurate. The author is asking you to use the 2-point table from 2 to 2.1. So we'll find those corresponding y values. I'll use a better one, since I ran back there. So y equals x cubed, 2, and we're going by 0.1. So we've got 8. Oh, I could have got that. And 9.261. So the derivative will approximately be 9.261 minus 8 over 0.1. 9.261 minus 8 divided by the 0.1, 12.61.